Now, please, groups 4 and 5. 4 and 5. Do you hear me?
Yes.
Yes.
And do you see this text? Graph coloring algorithm.
Yes.
So everything. Now, good morning, people. Good morning. Nice to have you all to be present at the lecture. I just want to remind you that today we have lecture number 13. Next time, lecture number 14, and on the December 12, we'll have the last lecture. The first hour will be devoted to something, just maybe revision or something, but the last hour will be the test. Just 10. Oh my, I will not talk so loud today. Just 10 problems. You can get up to 10 points. And at the exam, you'll get up to 30 points. And in total, the number of points that I'll give to you will be equal to 40. Please don't miss the test. I never repeat the test for those who miss it. And if you hope for a decent mark, you cannot afford to neglect those 10 points. Please. Also, I expect you to read carefully the remaining lectures. Now, I mean, devoted to combinatorics. Yourselves. Try and understand. We will talk about combinatorics today and next time, but maybe it won't be just enough time. You have to study yourself also. You are students now, and we have, hard times now. Hard times. You cannot expect to get all the all the knowledge from a beak of a teacher, as if we are birds, to be fed from mouth to mouth. No, you have to read something yourself and understand and so on. And if any questions, you are just invited to come for the consultations and to ask questions. But well prepared. Well, because frankly, I'm still in no shape. Okay, so last time we continue. Last time we discussed the problem of graph coloring, which is the problem assignment of labels to graph nodes in such a way that no two neighboring vertices are labeled with the same color, with the same number, if you like. For example, here, 1, 2 neighboring, their labels are different. And C, G, neighboring, the labels are different. So one thing, to use different colors for neighboring vertices, and another thing, to use the minimum possible number of colors. This is a practically important problem. Like in this example, here we just said that one of the possible applications of this algorithm is a problem of scheduling, um, operation scheduling or something. For example, at the plant, industrial plant, at some department or workshop, if you like, в некотором цеху, they have to make a certain amount of operations to complete the plan of production as soon as possible. Of course, it is advisable to do in parallel as many operations as possible. And this the problem of parallel scheduling of execution of these operations can be reduced to the problem of reduced to the problem of graph coloring. Here a vertex of a graph is an operation. The edge, there is an edge between two vertices if they cannot be performed simultaneously. And after that, for example, here, it is possible to divide into three groups. For example, this group, just vertex B, one vertex, color 1, vertices, 2 C and F, color 2, meaning that C and F can be done simultaneously. And A, D, and G, they get color 3. None of them are adjacent. And what? They can be, that's why these operations can be, different operations can be done in parallel. And after that, so we divide into the operations into 3 slots and taking into account the specific instructions. For example, that B should be after A, that F should be after B, and so on. We say that first ABG are performed in the first turn, this set of operations. B is done in the second turn, and CF are carried out in the third turn. Okay, we discuss it. I just remind you. But of course, it's can be done if we have just 6 vertices. Can be done without any algorithm. Look here, just plan a bit, experiment, and you'll get some variant of coloring. But if we have 500 or even more operations, the graph becomes very, very complicated. People, I have a request to you. Please, each of you, switch off your mics, because it creates a noise in the network. A noise in the network. So, in practical problems with many vertices in a graph, we need an algorithm. And this is a very interesting problem and a very interesting algorithm also. An efficient algorithm for correct minimum coloring of an arbitrary graph has not been found yet. And nobody knows if it is possible at all to design such an algorithm. But first, I just want to say a few words about what do we mean by an efficient algorithm. Efficient. It is a method or plan or procedure of solving the problem. It is a plan of a program, if you like. Okay. What is efficient? Efficient. It means that it can solve a problem for which the algorithm was designed of any input size, large or small, in acceptable time. In acceptable time. Because there are such algorithms that, well, they claim we are sure that the algorithm is correct, but if n, for example, is number of input elements is 50 or 60, it will take hundreds, maybe thousands of years to wait or waiting for the result. Well, it is not efficient. Here, the number of steps performed by the algorithm, and hence the time required by the algorithm, is expressed by a formula which is something like 2 to the power n, where n is the input size, where it is n factorial, where it is n to the power n or something. So these are nasty rates of growth of time and efficiencies. Such algorithms are not efficient, but algorithms where the number of steps is expressed by formulas like some constant, 5, 7, it doesn't matter. What it means, what matters that the algorithm requires a constant number of steps. Constant number of steps. Okay, or log some base of n, or n multiplied by log n, or n squared or something. Such algorithms with such number of steps, rates of growth of the number of steps and of the amount of time, because we understand that the more time, the more steps are required by the algorithm and the program, computer program. So such algorithms are called efficient, and they can produce a result in acceptable time, maybe seconds, maybe fraction of seconds, for any input size, be it 5, 10, or 100, or something, quite fast, acceptable. So efficient. For this problem, the efficient algorithm that solves the problem for any input size has not been found yet. And nobody knows if it is possible at all to have such an algorithm. And also what is important, if somebody I will drop it, this, just how to say, philosophy, just in a minute. Just a moment. And nobody knows if it is possible to design such an algorithm, but it was proven that if by the way, there are about 2,500 or 3,000 problems of this type. No efficient algorithm has been found yet, and nothing was proven that it is impossible. They are trying to find, but it was found that if somebody finds an algorithm that solves a problem like this graph coloring algorithm, then that algorithm with certain modifications will be able to solve any other problem for the set from the set of hard problems and the amount at the present moment, the number of hard problems are about 2,500 or 3,000 problems. All of them will be solved with certain modifications after some research and so on, but there will be no question anymore that if it is possible or not. Possible. So this is the interesting. Well, we are back to graph coloring algorithm. Existing effective graph coloring algorithms. Oh, by the way, just to complete it, I gave you in the labs, and maybe you don't know why. For labs, to design algorithm for such problems, generate for an algorithm for generating permutation. Of course, we cannot stop solving the problem until we generate all n factorial permutations. That's why it is an exponential problem, exponential algorithm. Also, we discussed the problem of Fibonacci numbers. There were three algorithms. The three algorithms for solving the problem. And what was the problem? Given the number n in the sequence, infinite sequence of numbers that are linked by the Fibonacci relation. And given the number, find the value of the number. It is possible to do either by a formula, by doing a constant number of steps, operations, if you like. So it is that algorithm requires constant number of steps. Or we can do it using the loop algorithm. Then it would be n. It will require n steps, also quite fast. And we saw it that a loop algorithm can produce the value of n quite fast. Well, never mind what is the n. Let it be 1,000 or more or something. Almost no time, several seconds, and here it is. And we could apply it. We could try and solve it using the recurrence relation. And there, the time-consuming step was the function call. With this approach, the number of function calls is, less than 2 to the power n, but actually 1.668 to the power n. So some constant raised to the power n, And there we discovered that with n equal 50 or maybe a bit more, it is working, and we cannot wait. We cannot get the result. We have to stop. So one problem is solved by different types of algorithms. Well, and here the type of the problem is just defined by the fastest algorithm that solves it. Here, it is with the Fibonacci numbers. It is the problem of can be solved by the formula, Binet formula, okay, or something like that. And in this case, it is considered to be effectively, this problem is effectively solved. And the problem, such a problem, is called polynomial. Polynomial. The number of steps or the time depend. The amount of time depends on the input size as some polynomial, as some power of n of the input size. Also, this is a nice problem. And I gave you the example of a traveling salesman problem. And here we found that fast, greedy algorithm doesn't solve it because it produces some result, but it may be not the shortest tour, but the longest tour. And if we try to solve it, how to say, to solve it really, to find the shortest possible tour, then it takes approximately n factorial steps. N factorial steps. If there are no restrictions on the type of the algorithm, if we start put restrictions, just impose restrictions on the type of the graph, then it may be faster. But we want to find it in general case. Okay. So that problem, the traveling salesman problem, it is similar to graph coloring problem at the same time. Now, we back to our algorithm. Existing effective graph coloring algorithms permit to obtain only an upper bound for the chromatic number of a given graph. In many cases, it is the actual chromatic number. The following algorithm here, greedy algorithm, designed by Welch and Powell in 1969, colors graph vertices correctly. It uses the number of colors which is greater than or equal to the chromatic number. So this graph allows to apply the number which is greater or equal than the actual chromatic number. The algorithm is based on a greedy strategy. At each step, it attempts to apply a current color to an uncolored vertex with the highest degree. Okay, let us see. So, greedy graph coloring algorithm. Input, undirected graph G. And you remember that a graph, it is set of vertices and set of edges. Output, same graph G, in which every vertex from this set, vertex V sub I, gets its color of V sub I, so that, not any color, but so that the value of the color is one of 1, 2, 3 max in this range, a number. And the value of the max is either greater or equal chromatic number of this G. Chromatic number, it is absolutely minimum number of colors. Max may be equal, may be greater. If V sub I and V sub J are adjacent, if two vertices are adjacent, the colors of V sub I is not equal to V sub J. These are the restrictions. And the graph, the algorithm is simple. Choose an uncolored vertex with the maximum degree. Maximum. And maximum degree, a maximum number of adjacent vertices, because a degree of a vertex is the number of adjacent vertices. And label this vertex uncolored by color 1. Second step, among all uncolored vertices, non-adjacent to vertex with the color 1, find the vertex with the maximum degree, and so non-adjacent to a vertex with color 1, and label it again with color 1. After that, repeat step 3, repeat step 2, to get color 1. In other words, we are trying to apply the same color as long as it is possible. But after that, when all the adjacent vertices and non-adjacent vertices get a color 1, we have to move to step 4, repeat steps 1 to 3, applying consequently. Oh my God, this here sequentially. Oh my God. Sequentially. Applying sequentially in sequence. Color 2, color 3, and so on, until each vertex gets its color. So, example will clarify it. Let us trace this 4-step algorithm using such a graph. G1. So first we find a vertex with the largest degree. It is L, because 1, 2, 3, 4, 5. Degree of L is 5, maximum degree. We assign color 1. Here it is. To vertex 1. After that, we get which vertices are not adjacent to A. This one, this one, this one, this, and this. Here, the degree of G is 4. It is 1, so we assign 1. And finally, among the vertices that are adjacent, that are not adjacent to L and G, and they are A and H, find the vertex A. A is adjacent, by the way, to A. That's why only H is left. We assign 1. Now, we are trying, we exhausted the possibility to apply color 1. Now, degree B, 2, which is 4. Degree F, 4. They are not, B and F, they are not adjacent to vertices with color 1. We choose vertex B to start, labeled by color 2. After that, M and A get color 2. Now, among uncolored vertices, F has the highest degree, F. It gets the color 4. After that, there is vertex C, but I cannot apply color 1 adjacent, color 2 adjacent, color 3 adjacent. That's why C gets the color 4. After execution of this algorithm, we can conclude that a chromatic number is less or equal of this graph, is less or equal 4, or equal to 4, less or equal to 4. Also, we can see that the chromatic number is greater or equal to 3. Why? Because there are cycles of odd length. For example, Mg, Gk, Km, odd length. That's why we cannot use less than 3 colors in this loop. So our chromatic number that we are looking for, less or equal to 4 or greater or equal to 3. So what is it? What is the exact minimum number of colors, 3 or 4, required by this graph? Our algorithm that we discussed does not give a precise answer for this question. The same is true for any other graph coloring algorithm designed so far. So look, the same is true for any other graph coloring algorithm designed so far. No precise answer. If we slightly deviate from the strategy of our algorithm of our 8-9, we can get a better variant of assigning colors to vertices of G1. Again, we start with L1. Okay. After that, we assigned 1 to G because it has the highest degree, 4. The greedy strategy requires that uncolored vertex G with degree 4 should get color 1, this one. Instead, it is C with degree 3 that is labeled by color 1. Well, it was my decision with color 1. This allows such a applying 1 here, allows to apply color 1 to 4 vertices, here and here, more. So for L, C, K, H algorithm, the previous algorithm applies color 1 only to L and G. Okay. Vertices of G are correctly colored. So now we can apply color 2 to F, to G, and to D, and color 3 to A and to M. That's it. All the vertices are colored by 3 correctly colored. No, by 3 colors. So we can conclude that the chromatic number is less or equal to 3. The presence of cycles of odd length prompts that the chromatic number is greater or equal to 3. From this and this, it follows that chromatic number is equal to 3. But now, for many graphs, Here I have specially chosen the shape of a graph. I was experimenting and so on. And I found such a graph that allows to be colored better than by a standard algorithm. For many graphs, the above greedy algorithm finds the upper bound for the chromatic number, which is equal to the number, not just greater, but which is equal, but which cannot be guaranteed. Which cannot be guaranteed. Okay, people. Do you have any questions? You don't? Well,
It seems no.
yes, because here it is, how to say, elementary. Now let us switch. What is it? Here, XP. We stop the oh my, oh my. Count. What is it? So people, in groups 1, 2, 3, do you see this lecture 13, basic concepts? Tell me, do you see it or not?
Yes.
Great.
Yes.
Just a moment. Now. Oh, I stopped everything. Damn it. Just a moment. Now, finally, it takes time, especially that I cannot concentrate with this COVID. If groups 1, 2, 3, see lecture 13. Tell me, please. If groups 1, 2, 3, see, you do?
Yes.
And group 4, 5, do you see this lecture 13?
No.
No.
We see lecture 12.
Excuse me, it seems that you forget to turn on the recording.
Well, it's not that important now, but do you see the lecture? So group 4 and 5 see only lecture 12, right?
Right.
Yes.
Oh my God. Now, group 4 and 5, do you see lecture 13?
Yes.
Yes.
Great. Uh-huh. Well, frankly, basic concepts of computer, with your permission, I will just hide it because I don't feel right. Basic concepts of combinatorial mathematics. Preliminaries, introduction, in other words, the field of mathematics that studies problems of how many different combinations subject to certain restrictions, restrictions, meaning подверженных определенным ограничениям. Сколько различных комбинаций, подверженных определенным ограничениям, can be made out of a specific number of objects. So this field of mathematics is called combinatorial mathematics. I must tell you that there is no short, concise, and precise definition of what do we mean by combinatorial mathematics or combinatorics or counting. Nope. They normally give it by a list of topics studied in this or that book or something. So they are very, very different in nature, those parts of combinatorics. But just to say something, at least to say something, I gave you here these three lines. Specialists in a broad range of fields, scientific fields, or have to deal with problems that involve combinations made up of letters, numbers, or any other objects. For example, the department head in a factory. А кто это такой department head in a factory? Начальник цеха на фабрике или на заводе. Head – начальник, department – цех, возможно. Там shop иногда называют department. In a factory has to allocate production assignments to machine tool operators, to распределить production assignments. Задание на выполнение работ оператором. Machine tool – это станок по обработке металла, как правило. Machine tool. This is one thing. There are different variants for such allocation of assignments. Oh, by the way, I will. The school principal draws up schedule of lessons and so on. So for a software engineer, combinatorics is important because its methods are used for analysis of algorithms' efficiency and also for solving problems of combinatorial nature. Well, people, now it's time for you and for me to make a break, to give some rest to my vocal cords, because I'm so sorry. I need a break. Need a break. Okay, we resume our lecture. Now, about some, well, notations used in the formulas later. A finite set M capital that contains n elements will be called a n set, and we shall write or denote it like vertical bus n equal to n, to indicate that the number of elements in this set n is equal to n, or cardinality of n. A subset A of the set M, which consists of k elements, A has k elements, will be called a k subset. N set is called ordered if each element of this n set is assigned a single position number I. Each element has a single position number I, or is assigned I positions from 1 to n. Note, to be ordered does not mean to be sorted. It is just having a unique sequential number. Now we come to the basic rules of combinatorics. I'm sure you studied them at school, but we cannot ignore them. We can never ignore them. The rule of sum. If a certain object A can be chosen in m ways, and another object B can be chosen in n ways, then the choice of either A or B can be accomplished in n plus m ways. So here it is just for two types of elements. Actually, here it is a set of objects or type of objects, and you can choose one of the objects in m ways, and here in n ways. A general statement of the rule of sum. If an object A sub 1 can be chosen in m sub 1 ways, an object A sub 2 can be chosen in m sub 2 ways, and so on. An object A sub k can be chosen in m sub k ways. Then the choice of either A sub 1 or A sub 2 or so on, A sub k, can be accomplished. So either this or this or this. In m1 plus m2 plus so on, m sub k ways. Note, we choose only a single element. A single element. Example. At the Kharkov University of Radio Electronics, students are trained at the computer science faculty in three specialties. At the system design faculty in 2 specialties. At the faculty of electronics in 2 specialties. At the faculty of computer hardware design. So faculty of computer hardware design in 2 specialties. At the radio equipment faculty in 2 specialties. So many faculties, so many specialties. In total, A full-time student can choose a specialty to learn one specialty in 3 plus 2 plus 2 plus 2 plus 2, which is 11 ways, assuming that a full-time student is allowed to study only at one specialty, at one full-time specialty. Okay, now another basic rule of product, basic rule of combinatorics, rule of product. If an object A can be chosen in m ways, and if after any such a choice, after any of choices, if we make one, after any such a choice, an object B can be chosen in n ways, then the choice of a pair A, B in that order can be accomplished in m by n ways. So if we take now an ordered pair, first object of type A and after that object of type B. A more general statement of the rule of product. If an object A1 can be chosen in m sub 1 ways, an object A sub 2 can be chosen in m sub 2 ways, and so on. An object A sub k can be chosen in m sub k ways. So if we can choose it, also, and if the choice of an object A sub 1, one of these, does not affect the number of choices of other following elements: A sub 2, A sub 3, A sub k. If the choice of A sub 2 doesn't affect the number of choices of elements A sub 3, A sub 4, A sub k, and so on. So if these conditions are met, then the choice of the ordered set of objects, A sub 1, A sub 2, and so on, A sub k, in that sequence can be accomplished in m sub 1 by m sub 2 by so on m sub k ways. So we use the rule of product. Example. Brand labels are designed. Brand. It is Levi's, Nike, and so on. All these are brand labels. Brand labels are designed. They should consist of one of 4 geometrical figures: a circle, square, triangle, hexagon. So 4 are geometrical figures. One Russian. Oh, why Russian? No Russian. Ukrainian letter and 1 decimal digit. How many such labels can be created? Examples of labels: V6, V6, and hexagon, K8, and so on. At the first step, we can choose a geometrical figure that can be done in 4 ways. We have a total of 4 figures. Then we can choose one of 32 I believe, 3 Ukrainian letters. Ukrainian letters. And finally, 1 of 10 digits. 1 of 10 digits. The total number is here. I just forgot to change it here, but here. 4 by 33 by 10, which is 1,320 combinations. Or runs. One runs. Maybe they are not much of an attraction, but still combinations. Another example. Given set A 1 to 3n, how many subsets, like empty subset, a subset of 1 element, subset of 2 element, etc. Is it possible to make of elements of the set A? Of the set A. When we create a subset of A, we consider element by element, and choose include current element in the subset or not. Like that. Set 1, 2, 3, n, and we decide here in, include, not include, in, not, one of them two. So we make n choices, 2 options for each choice, 2 options for each choice. A choice for element number I, for example, number 3, is independent of the previous and consecutive choices. One sequence of n choices for all elements. One sequence of choices of all elements from A, and we can call it n choice. N choice defines exactly one subset of A. One subset of A. For example, if here in and everything is not, then it is subset of one element 1. So there is a one-to-one correspondence between n choices and subsets. For example, n choice not in not corresponds to the subset to 3. By the rule of product, the total number of n choices and n subsets is 2 by 2 by 2, 2 to the power n. We multiply n times. So many subsets. We discussed about this formula for the power set of A from different angles so far we have. That's why we should be able to prove it in many ways. Permutations without repetitions. Permutations. The general statement of the problem is as follows. There is n set M, consisting of n elements of distinct objects. All of them are different. Often these objects are considered to be just numbers. How many K permutations, or another name for permutations, K arrangements, just arrangement in some sequence, arranged in some sequence. And ordered k subsets can be made out of these elements. Two permutations and the question. So we considered the situation, and the question was how many k permutations can be made out of these two permutations are considered distinct if they differ even by a single element or have a different sequence of elements. Example, we have to first of all to understand what do we mean by it. What do we mean by a permutation? M, A, B, C, two permutations, A, B, B, A, different sequence, A, C, C, A, B, C, C, B. So 6, two permutations. Three permutations of the same set, ABC, ACB, BAC, and so on. Also, we see that there are 6 three permutations. Such arrangements are termed permutations, the term for such a subset is called permutation without repetitions. And I remind you that the product 1 by 2 by 3 by so on by n is denoted by n factorial, is read n factorial. It is agreed, and you will see soon why, to consider 0 factorial to be equal to 1. 0 factorial be equal to 1. The number of k permutations of n distinct elements, distinct objects or elements, is denoted by a sub n high k. The number of k permutations of n. The first element. So we have n elements, and the first element of k permutation can be chosen in n ways. So any element of the original set, n ways. The second element can be chosen in n-1 ways, and so on. The kth element can be chosen in n-k plus 1 ways. Applying the rule of product, the necessary number of times we obtain the number of k permutations of n is equal to n number of choices for the first element by n-1 number of choices for the second, so on by n-1 minus k plus 1 number of choices for element number k. So we have such a product. What if we multiply this product by n minus k factorial, and of course divide by the same number? Then here we'll have n factorial, and here n minus k factorial. So this is the formula for calculating the number of k permutations of n distinct elements, like this. Now, let us experiment a bit. If n is equal to k, or k is equal to n, then we obtain here we have a substitute instead of k, n, and this is a special symbol here. It is n permutation of n elements, number of n permutations of n elements. n arrangements of n elements. Here, n factorial, n minus n, it is 0, 0 factorial. Well, this we agreed to treat as 1. That's why the total number is n factorial. The total number is n factorial of such arrangements. Okay. We continue. So you see the convenience and actually the appropriateness of this agreement. 0 factorial is 1. And in this case, our formulas will be just applicable for any value of k, from 0 to n. From 0 to n. Let us write down an important relation for the number of k permutations out of n elements. So a sub n high k, number of k permutations of n, equal to number of k permutations of n minus 1 elements plus number of k minus 1 permutations made of n minus 1 elements, and this number multiplied by k. So the sum of these two numbers. Relations of this type where the value is expressed through itself, but for a smaller value of the argument, are called recurrence relations or recursive relations. Well, we can prove this equality using just our basic rules of sum and product, And by the way, a majority of the following formulas that we are going to obtain later and prove maybe and so on, they can be easily obtained if we are skillful in applying the rule of sum and product. So we can prove the validity of this equality. So if element 1 does not belong to a k arrangement, well, let us see here. M, ABC. Now let us consider all the, just a moment, the elements without A, the 3 permutations without A. So they are made now only of B and C, but we can make in such a way 3 permutations, 2 permutations, B and C. And after that, number of such permutations is equal to B and C, 2. After that, we add A. A may be added here. in the first place, here or here, 2. It may be added in the middle, A, here. And A can be added at the end. So we can take the number of permutations that we can make out of here now we are talking about this. We are making 2 permutations out of 2 elements without A. And after that, put A into the right positions. There are K positions, which is first position, second position, third position. K. We are talking about 3 permutations, so third position. That is why we denote it by all permutations that we can make n-1 elements by k-1 element. And using the last element, which is not mentioned there, k position everywhere here. So these are permutations with, just a moment, with A. And here we are counting the number of permutations without A. Do we have? Without A, made out of n-1 elements. It is like this. That's why we may have either permutations with element 1, or here with element 1, or without element 1. K permutations. Either this or this. That's why we use the rule of sum to get the total number of such permutations. So once again, we can prove that this equality is true in such a way. If element 1 does not belong to K arrangement, does not belong, then it is a K arrangement of the n-1 set. Yes. Now n is large, K is not that large, that's why we can get some permutations without 1. Yes, the number of such permutations is like if the element 1 belongs to a K arrangement X, then this element can occupy K positions as I showed to you in it. And the rest of n-1 elements of M make K-1 arrangement in this arrangement X here. K-1 in this arrangement of n-1. Applying the rule of sum, we obtain the equality 3. Example. Just for the number of permutations without repetitions. In a studio club consisting of 25 persons, a president of the club, a vice president, and a treasurer, казначей, are elected. In how many ways can this choice be made? It is like this. A, either 25 factorial divided 25 minus 3, as it was, either by 25 minus 3 factorial, or we can just, annihilate unnecessary elements here, and it is 25 by 24, 23 ways. Now, combinations without repetitions. Here, this is the number of subsets which are ordered, where we care for the sequence of elements. Combinations without repetitions. Let M be set of n elements, distinct elements. K combinations are unordered K subsets of M. Two K combinations are different if they differ at least by one element. At least by one element. Example. Different two combinations of set N, which is ABC, are as follows: AB, AC, BC. Two combinations. The number of K combinations that are generated out of n distinct elements is denoted by. By the way, and what is the number of three combinations of this set? Three combinations. It is one, because we can make only one unordered subset of the elements out of here. And the number one combinations, it is of course a three combination, three such combinations. The number of K combinations that can be generated out of n distinct elements is denoted by C sub n high K, or we read it n choose K, given an element choose K, that's it, n choose K. Let B1, B2, Bk, and you see curly braces, that's why unordered sequence. We don't care if it is B2, B1 or B1, B2, it is still the same unordered subset with some K combination of n distinct elements. Rearranging this subset in all possible ways, we obtain of it K factorial different K permutations. K factorial, if we rearrange K permutations. All permutations obtained in this way are different. And each K permutation can be obtained from some K combination. So here we have such a set or collection of items. After that, we permute them, get K factorial sequences. Okay, made of these B1, B2, Bk. After that, we add here Bk sub plus 1 instead of Bk. Okay, again, we can get n factorial permutations. All permutations obtained in this way are different, and each K permutation can be obtained from some K combination in this way. That is why, if we talk about the number of permutations, number of K permutations that we already know, it is equal to number of such unordered K subsets and how many ordered K sequences we can make of such a subset, multiplied by K factorial. Here the number, we know it. Here the number, we know it. We are interested in this number. That's why, of course, we n choose K divided by K factorial, which will be equal to C sub n high. C sub n high K is equal to this ratio 4. From this formula, so from this formula? It follows immediately that C sub n high k, or n choose k, is equal to n choose n minus k. Because here, if we substitute n minus k, then this, instead of k, here we have n minus k, and here it will be k. Let's see. This equality phi is called property of symmetry. Property of symmetry. Okay, numbers. N choose k, where k, now the number of elements in the subset is less or equal 0, or where k is greater than n, as well as n factorial that we agreed before so far, have no combinatorial sense. No combinatorial sense. But it was agreed that n choose 0 is equal to 1. N choose k equal to 0 if k is less, this k is less than 0, or greater than n, greater than n. So this remember, and it is important because if we substitute such values into the formulas, combinatorial formulas, they will be applicable to all kinds of objects. For k combinations, such recursion relations hold true. For k combination. C beta n choose k, or C sub n high k equal C sub n minus y k high k minus 1 plus C n minus 1 C sub n minus 1 high k. And here just I explain that this we can treat it as the number of combinations with element 1. That's why everywhere here 1 is present. So the job is to choose k minus 1 out of n1 minus 1 elements. And here the number of combinations without 1 element. So we are making k subsets in the set from where we exclude element 1, where we have n minus 1 elements. That's why this is the formula. Example. It is necessary to select 3 people out of 25 to go to some meeting. In how many ways this can be made? And by the way, here there is no leader, no deputy leader, no nothing, just you 3. You are equal, you have equal rights, you have equal duties. Please go sit there, and after that, tell us what was discussed there. That's why there is no ordering of these 3 people. In this case, we are not interested in the sequence of names in the list of a delegation, quotation mark delegation. That is why we consider 3 combinations. So 25 choose 3, we substitute it into the formula, and after that, see that 2,300 ways, 300 ways. This is a possible number of choices for 3 people out of 25 if they don't object attending meetings. But here permutations, because a president, it is a position in the sequence. President first, vice president second, treasurer third, and if we put somebody in the first position, he or she will be the president, and so on. That's why here positions are marked. That's why we talk about. Okay, people. At first, I started to talk faster, but very soon my vocal cords were down. Do you have any questions, people?
No?
No.
No. But
It seems that no.
very nice. What the lectures on combinatorics, they are typed in simple ways. In a simple way. The problems that I'm going to give to you during a test and the exam, they will be within the methods discussed there. That's why, if you read carefully, if you look at the problems in tutorials and so on, there will be no problem for you, no difficulty for you in solving combinatorial problems at the exam and in getting a good one. Please read them yourselves. I'll do what I can during a lecture. But you know, we had a major force this semester because I had to change the sequence of lectures quite frequently in order to to prepare you somehow for labs and tutorials. That's why, well, you were supposed to read and study yourselves also, as any student should. Well, okay. People, if you have questions, you may join the consultation at 1:10 today. But please think carefully about your questions, ask, and so on, because frankly, for some unknown reason, today I feel worse than yesterday and than Saturday. I don't know why. Maybe because only on Saturday they stopped giving me injections and some other things. Well, injection. Humorous. Okay, thank you. See you.
Thank you. Thank you. Bye-bye.
Bye-bye.
Thank you. Bye.
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 Sit.